Now it's 35 past 3 p.m. in Beijing and 35 past 10 a.m. in Moscow. It's my pleasure and a great honor to introduce today's speaker, Professor Vassily Manturov from MIPT. He is also the organizer of our seminar. He will tell us virtual theory methods in topology, part 2, parity and cobordisms in the cylinder. Let's welcome Professor Vassily Manturov.
Okay, thank you very much for the invitation. It's a great pleasure for me to speak here, as always. And today I'm going to talk about the second part of this theory. We started together with Kim Sang-jong and Kim Sera, my collaborators. And as in the first part of my talk, I was talking about some more abstract objects like free knots. Today I'm going to talk about more topological objects and actually knots in the cylinder. And the invariants I'm going to construct today are very simple to construct and easy to compare. And what's important, they are cobordism friendly. So why virtual knot theory methods? Actually, because in virtual knots, we first found the notion of parity. And actually, this notion revolutionized virtual knot theory and led us to the discovery of picture-valued invariants and actually many other invariants. In fact, parity considered for virtual knots is a very nice property. Well, in some sense, we can say that if we have something non-trivial, maybe homologically non-trivial, then it can't disappear for free. And actually, as in some higher dimensional topology we count, maybe with some signs, if we try to count some intersections between homology classes, cohomology classes, evaluations, or just we count some discrete things, then under proper conditions, this count gives us invariance. And in classical knot theory, it doesn't appear to be very much visible because, well, in classical knot theory, there are lots of even things, even which can be something like disappearing cycles, trivial cycles, and something which we should not much care about. But we really want to have something odd, and if we count some odd points, we can get invariance. And here I want to say some words about the parity bracket, and these are actually picture-valued invariants. I told a lot in my previous talks, and actually in many previous talks. And the parity bracket is something which allows us to realize the following principle. The following principle can be called something like local global principle or something like principle of free groups, so that in an object which is locally minimal is globally minimal, in the sense that if we have some topological objects, say, and these topological objects are equivalence classes of some diagrams, modular moves, and there is no way to decrease the topological objects in one term, then it's minimal. So this could be a dream which definitely doesn't work in higher dimensions because, well, the word problem and other problems in group theory cannot be solved. Actually, this dream does work in free groups and actually in hyperbolic groups and many other groups, say small cancellations and others. And now we want to realize it in knot theory. This doesn't work just for knots by themselves, but let's try to do some other topological problems. And actually, the parity we introduced that time, maybe it was something like 2009, was a way to construct picture-valued invariants. So what do I mean by picture-valued invariants? actually assume we have a knot diagram. Then we can say, okay, here we have a knot diagram, and let's construct an invariant of it. So people can say, well, we can count the number of colorings. Or people can say, let's introduce some homology theory and count some homology classes. They will have, say, 2 gradings. Or people can say, okay, let's construct a group corresponding to a knot. Well, I would say that if we have just a number or even Betti number, this can say us something about the knot, but not as much as we can say in the case of a free group. For a free group, we can say, okay, the minimal reduced representative is unique, and this more or less solves all the problems in free groups. I mean, word problem, conjugacy problem, and that's easy. And actually, I want to have something easy for knots. So what can we consider instead of this minimal unique representative? Actually, we can pretend to have a minimal knot diagram, and we want to pretend this minimal diagram to be unique. And actually, you see, if we have lots of even crossings, then it can even happen that some of them can be canceled by Reidemeister 1. So actually, you see, even things can be canceled somehow. But assume I want to consider only knot diagrams modular Reidemeister 2 moves. It's easy to look at such odd diagrams, and it's easy to prove that such diagrams and such objects I call pre-knots, they have a unique minimal representative, which is obtained by just decreasing moves. So in some sense, free knots, in some sense, if we consider framed graphs modular just Reidemeister 2 move, such framed graphs have a unique minimal representative. And actually, if we look just at these objects and forget about Reidemeister 1 and Reidemeister 3 moves, those objects will be classified by its minimal representative. And actually, as many people in topology know, there are invariants called state sums. And now I introduce yet another state sum, but which is somehow not similar to any, say, Kaufman bracket or state sum invariants of 3 manifolds. Actually, I want to undo even crossings. So I want to say that if I have something which pretends to be trivial, I mean even thing, then we can, well, let's undo it somehow. And there is an old theorem that if we take a certain sum, I don't want to decipher it completely, then we can have a linear combination of diagrams, and these diagrams are modulo Reidemeister 2 move. Actually, this parity bracket, if we look at it more carefully, if it has only odd objects, then this parity bracket realizes the following principle. If a diagram is complicated enough, then it realizes itself. As a theorem, this looks like if all crossings of a free knot diagram are odd, and there is no way to kill 2 crossings by a second Reidemeister move immediately, then this diagram is non-trivial. And moreover, any diagram equivalent to that will be will contain this diagram as a proper as a subdiagram in the sense of smoothness. So actually here our knots become similar to free groups. And in fact, there are lots of generalizations of this parity bracket, which realize the same principle in the domain of virtual links and virtual knots. And actually, all those principles require a sort of parity or a sort of non-trivial homology. Well, and now you can ask me, well, where to take such parities if we want to deal with the classical knots? Well, actually, parity appears everywhere when we have some non-trivial Z2 homology. And for example, it appears in knots in the full torus or in the thickness cylinder as we have here. And now you can ask me the question, well, what about just knots in this theory, and why did it take 10 years or even 12 years to realize all those theories for knots in the thickness cylinder? Actually, there are several problems and there are several obstacles to overcome this theory. One of them is that actually, if we take diagrams drawn on the cylinder, so they are too easy. Actually, if we don't take into account, who is over, who is under, then just curves on a cylinder, they are classified by their 1D number. But if we do take something into account, I mean, over and under crossings, this will be a whole knot theory. So in fact, in order to realize some parity theory, and in order to realize and construct invariants which have fancy properties, we should somehow take some other point of view and maybe not deal not exactly with parities, but with something else. And what about something else? In fact, I'm going to deal with free knots, invariants valued in free groups. And actually, there are several reincarnations of the main principle of my work. The first one is the parity bracket. So when I have invariants of objects valued in diagrams of this object, and my favorite formula looks like that. So if we have a diagram which is odd and maybe reducible, then its bracket equal to itself, meaning that if we have something odd, then we have nothing to undo. So actually, this is similar to free groups. So if we have a reduced word, we have nothing to cancel. And in this case, we have a minimal diagram. So this is one reincarnation of our principle. The other reincarnation is, as you can guess, a free group. So actually, we have free groups on n generators, but actually, I will standardly abuse the notation. And I can also, by using the word free, I will sometimes use free products of cyclic groups. And actually, so something like, mostly I will use something like free products of some Z2s, and maybe even I will consider some finite index subgroups or groups commensurable to free, because you see, if we look from far enough in Gromov's sense, in the sense of hyperbolic theory, then from far enough we don't see anything like finite. So we don't see any difference between a group and its subgroup of a finite index. And for example, if we look at some infinite dihedral group, then from far enough it looks like Z. So actually, this is the other reincarnation. And actually, if we look at this theory, then it will be very much cobordism friendly. I mean that we can often raise the dimension. We can create invariants of knots which detect knot sliceness and detect in a very easy manner. So just a group element, if it's not trivial, then the knot is not slice. Not only non-trivial, but also non-slice. That's important. And the third reincarnation will be what I call secondary and ternary and other indices. So actually, what do I mean by indices and what do I mean by parity? Well, you see, we may try to count something non-trivial. What do I mean by non-trivial? Well, we can imagine that we count some homology classes. And our first rough approximation was to count homology classes which are somehow non-trivial mod Z. Mod Z2, excuse me, mod 2. Okay, so there are some classes which are non-trivial mod 2, but there are lots of other non-trivial classes which are trivial mod 2. But how can we see them? Well, actually, here we can introduce something called secondary indices, ternary indices, and so on. Well, here I want to mention a very famous lemma or theorem due to Gauss, and maybe this theorem was one of the first results in knot theory. And the theorem is as follows. Assume we have a knot, and we can draw a diagram of a knot. Okay, so let's draw something on the plane. So, for example, this is the curve corresponding to the, well, this is a curve. And let's consider what is called the Gauss diagram of this curve. This means that we travel along the curve, and whenever we meet a double point, we enumerate this double point, and then we create a chord diagram where two instances of the same double point are connected by a chord. So, for example, here we have something like 4 chords, and one is connected to 6, 2 is connected to 7, 3 is connected to 4 like this, and 5 is connected to 8. So we have this Gauss diagram. And you see in this Gauss diagram, all chords are even. Even in the sense that each of them intersects evenly many chords. And actually, this was a lemma by Gauss. So if we try to draw a curve on the plane, then all intersections will be even. And this can be given as an exercise to students. And actually, Gauss made a mistake. He thought that this condition of parity is necessary and sufficient. And this mistake, actually, when great people make a mistake, this often gives rise to very powerful theories. And actually, there were lots of criteria of planarity for such curves. And actually, parity is just one situation of non-trivial curves. And there are many other curves. And now I want to look more closely at such a diagram and convince you that not only parity can give you something non-trivial. For example, I can draw such a chord diagram. Well, and you see, if I look at such a chord diagram, then here I will have 4 chords, and 2 of them, let me draw them in red. 2 of them are odd, so that each of them intersects just 1 chord, and 2 of them are even. But in some sense, those 2 even chords are non-trivial because, well, if we forget about odd chords, then those formerly even chords can become odd. So in some sense, there will be a sort of parity hierarchy. I don't want to dwell into that notion just now. We will consider it. Later in more detail. But what I want to say is that there is a whole collection of indices or whole collection of parities when next indices correspond to they appear once previous indices are trivial or something like that. So there will be a whole collection of indices which are extremely easy to calculate. They're completely combinatorial and which give rise to invariants of knot. Well, again, those things are very easy. in the sense that they are easier easier than free groups. And actually, two non-trivial things can cancel if they can cancel, then they have the same indices, primary, secondary, ternary, whatever. And this gives us lots of abstractions. And again, like free group valued invariants, those things are parity friendly. So in some sense, these three reincarnations, picture valued invariants, and free groups and indices give us just a very large information about a knot, which can grow somehow exponentially with respect to the number of crossings, and which can be coordinate friendly. Well, and actually one more slogan, if we have some Z2, we can find secondary, ternary, and other things, and we can get free group invariants. So just Z2, a class in homology, can give rise of something, and we will get something of exponential growth, which is very easy to work with, and which will give us to some very strong invariants. These strong invariants are easy to compare because they are just elements of free groups. We get a reduced word, which gives everything, and they are related to cobordisms. And we can get free groups or indices, primary, secondary, and ternary, and everything appears if we have just one Z2 or maybe one integral valued index. And I will abuse the notation a lot. I will call free products of Z2s just free groups. I will switch from Z2 parities to Z indices, and you will see that actually we can create many hyperbolic things and many groups with exponential growth and many indices, even if we have only Z2. Okay. Well, now I want to be more concrete, get back to the earth, and here is the essence of my talk I gave at many seminars, for example, at the seminar by Luke Hoffman and Roger Fan, and actually my talk will consist of two parts. My talk I gave elsewhere was devoted to the invariant which we discovered jointly with Kim Sang-John and Kim Sara, and that dealt with invariants of long knots in the cylinder, and those long knots invariants are valued in free groups. Well, and actually, when we looked more carefully at those invariants, we saw that actually there are sliceness invariants. They give sliceness obstructions, and they're very much cobordism friendly. But you see, in order to realize it for groups, it can take some more effort. So today, the second part of my talk, which is novelty for this talk, which hasn't been presented elsewhere, the second part of my talk will be devoted to invariants of secondary indices, which are cobordism friendly. Well, of course, what we have for long knots can be also made cobordism friendly, but it requires some further techniques. For example, if we have long knots, then we can get words in the free group. And if we want to have compact knots, closed knots, then we should do something, for example, valued in conjugacy classes. So there are some minor details. And let me start creating an invariant and formulate exact definitions and exact theorem. Okay, so for usual knots, we can get long knot diagrams from R to R2, and it's very well known that the classification of compact knots in R3, excuse me, is the same as classification of long knot invariants. Actually, knots in R3 is the same as knots in S3. Well, and actually, we can, if we created Gauss diagrams for knots, we can do the same for long knots. And the only difference being that for long knots, our Gauss diagrams will be drawn on the line. So we do something like that. So assume we have a diagram, and then assume we have a Gauss diagram. Then we just cut it at some point and stretch the ends. Okay, and now you see here I drew a diagram not on the plane, but I rather drew a diagram in the cylinder. What do I mean by a diagram in the cylinder? Well, you see here, I have a lemon-like surface, which is this topologically the same as the cylinder. And you see here by crossings, I mean only crossings which are with respect to the projection to the cylinder and not to the plane. So here we have some dotted lines on the on part on the back side of the cylinder diagrams, and those things like here, they do not count as crossings. Well, you see, if we deal with diagrams inside just the usual cylinder, and those diagrams are not long, so for such diagrams, everything is somehow the same as for the case of the plane. What do I mean? Actually, if we draw a couple of circles here, and if we get an annulus, and topologically an annulus is the same as the cylinder, and if we try drawing and if we try drawing some diagrams here, then the corresponding Gauss diagrams will be just planar. So the Gauss diagrams for this annulus are the same as Gauss diagrams for just usual knots. And actually, here, the first thing we did is we considered long diagrams inside the cylinder. And by long, actually, we meant that our diagram starts from one end and ends on the other end, and actually starts at one boundary component and ends at the other boundary component, and that makes our diagrams topologically non-trivial. So in fact, if we want to close up this diagram, then this diagram will appear. It will appear on the topological torus. I mean, we can identify those two boundary circles, and we can identify one with the other, and we will get S1 times S1. And actually, this is a way to say why we get something more than just curves on the cylinder. But actually, we deal with long knots, and this theory has a lot to do with knotoids. And actually, here we will create lots of non-trivial invariants, but I will give just some of them. And in the second part of our talk, we will deal with compact knots, and in the first part we will deal with parity, and in the second part we will deal with the index. So actually, they both originate somehow from the Z2 homology. So for the cylinder which is not thickened, we have Z2 homology, and for the torus we have Z2 homology. And here you see I drew a Gauss diagram for this knot, and the Gauss diagram on the line looks like this. And here I use red color for even chords and black color for odd chords. So in some sense, black things are something similar, something serious, which we have to count. And I want to count them by letters, and there will be even letters and odd letters. And usually I will use the letter A for even chord ends, and I will use some letters like B, C, or maybe B prime, or maybe B to the -1, C prime, C to the -1 for various types and sorts and species of odd chords. Actually, there has been a lot of upgrades of this result, and I originated from abstract objects like 3 knots, and now I can deal with knots in the thickened cylinder, or if you wish, knots in the full torus. And I want to do the following. With any diagram of a knot, I associate a certain word. And then I want to trace what happens if I perform Reidemeister moves to the knot diagram. And applying Reidemeister move, of course, I will do something with the words. And if I want to consider, if I want to get a group valued invariance, I should take care of equivalences in those words. And actually, those equivalences will correspond to Reidemeister moves. And surprisingly, or maybe not so surprisingly, the groups will be almost a free group. The group will be almost a free group. So you see, here I want to distinguish between odd chords of first type, position, and so on. You should not memorize all those things. They are all written in the slides. So the main thing is that odd chords are B's or C's, and also there are some species of those chords which correspond to Reidemeister moves. And actually, here is a first way of making distinction between different species, I would say, of odd chords. A chord can be odd, but this chord can intersect evenly many odd chords, or it can intersect oddly many odd chords. And if I look at, say, adjacent chords which can be cancelled by a Reidemeister 2 move, then such chords will be of the same species. But this can change if you perform Reidemeister 3 move. So let me draw something on my screen. And for example, I can look at an odd chord and I can say, okay, this is odd. And for example, I can have a Reidemeister 3 move. And actually, one can easily check that if we have a Reidemeister 3 move, then either all chords are even, or 2 are odd and 1 is even, and we can have something like this. And you see, if I perform this move, then the resulting diagram will look like this. So all chords which will switch their adjacencies. So those 2 guys will be odd, and you see that will be even, but here somehow the property of this chord intersecting evenly many even chords will change. So sometimes our letter will change under the Reidemeister move, so this will give rise to some relations. But if we can look at some further properties and say that in some sense the chords will not change. What does it mean the chord will not change? Well, this means that we can look not only at the number of chords which intersect this given chord, but we can also look at the position. So I don't want to give too many details, so they're written here. We will have many B's, many C's, and so on, and many B to the -1 and many C to the -1, and only A for even crossings. And then we can write down the word. The word is written like this. And actually, A's will correspond to red chords, which are even, and C's and B's will correspond to chords which are odd, and that's it. And the main theorem is that the group we give here, this group is called G double prime, by reason that in the beginning we had some group G, and here we upgraded many times. And the map, which is just writing down the word, will be a well-defined map. So this is a theorem. This is a standard theorem, and actually the proof is standard. So we just look at Reidemeister 1, which is the cancellation of 2 A's, Reidemeister 2, which is a cancellation of some chords which have to be, some letters which have to be canceled, like a squared equals 1, or maybe bb to the minus 1 equals 1, or maybe cc to the minus 1 equals 1, and which has, we just have to look at Reidemeister 3, and that's it. Okay, now I want to say that this theorem can be more infinitely upgraded, so we can introduce further indices and many other things, and we can create many other groups, but this is already enough to show that we can have very non-trivial example, and this one is already non-trivial. Well, of course, many A's can be canceled here, but you see C, B prime are not canceled, and actually we see that we will have at least 2 chords. But sometimes we can make a distinction between even chords and get further parities of indices, and for example, say that not everything will cancel here, okay? Well, not all A's will cancel here. Okay, and now I want to say that many things, well, okay, so these are generalizations of those.
Sorry.
Okay.
Very sorry. Yeah, just before you go through the proof and so forth, I sort of, yeah, okay, so could you just clarify me for me again, the notion of oddness and evenness of the chords again?
Yes. So the chords are even. A chord is even if it intersects evenly many chords, and the chord is odd. Yao Lao Shi Ni Hao. And now I'd like to return to the very beginning and just say some words about the outline of the talk. So actually, I'm going to introduce parities, and parities are something which originates from some non-trivial Z2 homology classes. And having these things, I want to introduce invariants which are valued in free groups, or maybe free products of Z2s, or maybe some groups which are commensurable with the free products of Z2s. So actually, this example is more topological than the example I gave at my first talk here when I was considered free knots. So here I want to construct invariants of knots in the full torus. And invariants of those knots will be valued either in free groups, or in free products of cyclic groups, or well, in something I call secondary indices. This will appear a bit later. And in some sense, they realize the local global principle, well, which means that if the invariant is smaller, irreducible enough, like a reduced word in a free group, then it's globally minimal. It cannot be reduced. So the main features of my invariants are as follows. So having just Z2 homology, one can create something called parity, which gives invariants which enjoy the property of exponential growth, like free groups, and they're very easy to work with because the word problem, the conjugacy problem for free knots is just for free, for free groups is just for free. We get very strong invariants, and this is realized only in a very simple situation, knots in the thickened cylinder, or knots in the full torus, and they're very much cobordism friendly, so we can raise the dimension by 1, and we will see that we have sliceness obstructions for knots in the full torus. So we have sliceness obstructions, and we know that sliceness plays a crucial role for smooth topology in dimension 4. And actually, here for the second part of my talk for cobordism invariants, I will rather work with something I call primary, secondary, ternary indices rather than with free groups, because it's just simple and technically easier. And so the slogan of today's talk, just find some Z2 homology and we will have lots of powerful invariants, which are cobordism friendly. And okay, so actually, more or
sorry,
less, yeah.
Just to get a bit of clarification on what it means to give rise to lots of groups which are of exponential growth.
Well, free products. Well, okay, just take a free product of 2 copies of Z2. So, I mean, if we have 3 copies of Z2 and write, say, words of length n, there are exponentially many.
Exponentially growing, sure.
Yeah,
but
yeah.
When you said give rise to lots, do you mean that there are many subgroups of the not complement group?
No, I mean that we can just upgrade these groups in many ways. So you see here, here it's already very complicated, but I don't want to say much in detail actually. So here I just show a couple of examples, and this will be the beginning, the end of the first part of my talk and the beginning of the second part. And actually the idea is very easy. I take a note and I write down a word according to some rules, and this word turns out to be an invariant valued in some group, and this invariant and this group is almost free, and so actually we can upgrade this group by looking not only at even chords or odd chords, but we can make further distinction between even chords by looking at something like how many even chords are intersected of those with that one, or how many odd chords are intersected with another one, and so on. So we can make a distinction and create, say, okay, this knot has, for example, 5 B's and 7 C's and 13 B primes. And we can say, okay, we have a whole collection of numbers. We have a whole collection of indices. And more or less the collection as it is a knot invariant. So we can write it either in the form of a group invariant when we have nothing to cancel. So the reduced word is an invariant inside this free group. Or we can say, okay, we have just many indices. And this will appear in the second part of my talk. I will say more about indices, and more or less we can say, okay, this crossing is an elephant, and that crossing is a crocodile, and an elephant can cancel only with the minus elephant. And actually this means that once we have some very simple source of Z2 homology, we can create further and further and further indices, species, and other invariants. And this may be a beginning of the dream of getting further distinction between intersection homology valued in free groups, or maybe further distinction of non-commutative characteristic classes and other things in topology I will mention in the very end of my talk. But today I'm discussing some very concrete invariants of knots in the full torus. Actually, here is a Kelly graph of some group we deal with. So this is more or less the free group with 2 generators. Actually, not quite, but it contains 2 parts, with the red part and the blue part. So actually, the subgroup of index 2 here is just the red part, which is free. So these are the groups where we have invariants valued in. And actually, here are some more. Yes?
Are these purely group theoretic invariants, or are they meant to somehow be quasi-asymmetric, I mean, heuristically quasi-asymmetric to the geometry of the knot complement?
Somehow we can say, okay, this knot goes far away. I mean, if we travel along the knot, we can say, okay, we have something like some intersection index. I don't know where. Maybe in some covering space or something like that. And this is something like a collection of Z2s. And we can say, okay, starting from these Z2s, we can create some other configuration space and then we can distinguish between further Z2s. But if I go just along the topological way, maybe I can describe all those invariants purely topologically by saying that let's take a tower of covering spaces or something like that. But this will be enormously huge. And here I just give a formal definition when I use just letters, and the group is more or less free. So
okay, thanks.
Okay, here are some words in the free group, and we can compare these words and say that these groups, these elements are non-trivial. Just look, they give different paths in the group. But what is interesting, and what I want to talk in the second part of my talk, is that it's not only trivial, but it's cobordism friendly. Cobordism friendly, which means that it gives a sliceness obstruction to knots in the full torus. And actually, for free groups, we can get many things for free, meaning the following. For example, in knot theory, you can ask, well, there are some invariants which can be very much respected if, for example, they can recognize knot invertibility. For example, we invert the orientation of the knot, and we compare the initial knot and the final knot. Are they the same? So for free groups, we can get an obstruction for free because we just invert. We can just invert the reward. So just look at some notation. Maybe it's not the best notation, but somehow we write the letters in the opposite direction, and just see, well, if it's somehow palindromic, if it's not palindromic, then we are sure that the knot is not invertible. And there are some other effects like mutation, and this mutation also goes for free. We consider two words in the free group, and having a mutation for knots, we get a mutation for group elements. Okay, we can get lots of examples, and more or less such examples of non-invertibility and other things, I would say, have probability 1 as the number of crossings tends to the infinity. Well, if you write a random word of a very large length, so you cannot expect that it should be palindromic. So if you draw a very large knot, you should not expect that it will be invertible. So, and here you can see for free, because for free groups, it's a piece of cake. Okay, and now I want to say that for free, what you can have here for free is a sliceness obstruction. You see, you see, if we have a sliceness obstruction, actually, you don't need anything, maybe except for the winding number. So if you have a cylinder, then you can have Z homology classes. Z homology classes of whatever intersections, and those Z homology classes can give rise to groups. They can give rise to groups, and we can construct group-valued invariants. But now I want to say something more, not in the language of groups, but in language of secondary indices. So maybe I can just say a couple of words like this. So assume we have a crossing which is homological, which has something like 5 times the generator of homology groups. So assume we have a way of indicating that it has index 5. Then it can be canceled with something which has also index 5, and in some sense this is positive and this is negative. So of course it's easy to imagine that we have such a setup. But later we can say, okay, this is 5 and this is 5, but possibly this 5 intersects a chord of well, let's consider another 5 here. And we can see that this 5 and that 5 are not the same, but incidentally the same. Because, for example, this 5 intersects something which is called 6, and that 5 does not intersect something which is called 6. Well, I will make all those statements precise, but then I will say that there are many other species of chords, and in some sense this is similar to free group valued invariants, and in some sense these are similar to those cats which appear in categorification, because we can say, okay, this is an invariant, and in some sense we can say, okay, we're just counting some characteristic of that cat. For example, we can count, well, I don't know, we can count its legs and say, okay, this cat has 4 legs and 4 is 0 mod Z2. But we can be more specific and say that between his legs, he has something like his back or his tail or whatever. And in some sense, we cannot cancel this leg with that leg. Because, well, and we can construct the whole picture. We have a 5 chord, we have a 6 chord, and we can have another 5 chord after the 6 chord, and this is in the group theory language. And we can make such languages easily once we start with some non-trivial homology. So the slogan is, having a non-trivial homology, we can consider very powerful. Okay, and here I would start with some winding number, and we can get secondary invariants. And this paper actually did not start from nowhere. Actually, there was a paper of mine maybe 9 years ago when I constructed some sliceness obstructions for free nodes. But actually, sometimes people do not trust free nodes or virtual nodes very much, because they say, okay, these are objects which are abstract. Today, I'm talking about very concrete objects, nodes in the cylinder. And actually, the ideas which appeared that 10 years ago, they work. Actually, here we are just accurately drawing a node diagram of the cylinder and having crossings. So we project our node diagram to the cylinder, and having crossings here, we can associate some winding numbers to that crossing. So what do I mean by winding number? Well, if we start from a crossing, we can go along the knot and return to the initial position. Well, you can say, okay, we can go this way or we can go the opposite way. Well, will we have the same winding number? Well, actually, the same modulo the winding number of the knot itself. So, for example, if the winding number of the knot itself is 10, then we can have one winding number to be 3 and the other be -7. Actually, we can get lots of invariants when the winding number is 0, but sometimes it's technically easier to work with the situation when the winding number is non-zero. Okay, and actually, I want to consider some. Crossings and some further indices, which can be treated as follows. So here we have some formal description of what's going on, and here is the formal definition. But non-formally, I'd like to draw a picture again, and actually. What I'm doing now is as follows. So assume I have a chord which has winding number 7. For simplicity, allow me to think that the whole winding number is 0. So assume this is winding number 7. And then if I have a third Reiter-Master move, actually the third Reiter-Master move is the main non-trivial thing here, because the second Reiter-Master move means just a cancellation of similar objects, so they both have to be 7, for example, if one of them is 7. And if I have such a Reiter-Master, such a triangle, such a third Reiter-Master move, then, for example, if this is 4, then that one is 3. So they sum up to 0. So if we take this, then 4 plus 3 minus 7 is 0. And if we perform a Reidemeister move like this, so they share they switch their adjacencies, and this means that if I have 7 here, then it can switch the adjacencies with 3 and 4 at the same time. So what does it mean? Actually, this means that if I look at this 7 chord, for example, here, I can look at its adjacencies with all 3s and 4s, and I can look at this parity. I can look at 3-4 parity, which means that for these 7 chords, I can look the parity of chords with index 4 and the parity of chords of index 3. And well, of course, I take it mod 2. And this index will not change whenever I apply Reidemeister 3 moves. So this number will not change. And I can do the same for example, 5 and 2, and the same for 6 and 1. So this means that any chord of index 7 can have at least 3 indices. So one of them is responsible for parity of 1 and 6, the other is responsible for parities of 2 and 5, and the final one is responsible for the parity of 3 and 4. So actually we have at least 8 species of chords number 7, and if we have 2 chords which can potentially be cancelled, for example, like this, 7 and 7, so which can be potentially cancelled with by a Reidemeister 2 move, they should have the same 3-4 index. So they should have the same triple of indices, so they should belong to the same species. Actually, we can proceed and we can get not only secondary, but also ternary indices and much more. But even here, you see that you can construct a large picture of further secondary, ternary, and other invariants, just starting from one index, which is just nothing but a winding number. Okay, and more or less now, what I want to demonstrate is that such invariants, so here what you see is just the collection of those 7, 1, 6, 2, 5, 3, 4. Okay, and now what I want to say is that this is cobordism friendly. Actually, this slide shows that what we have here is not invariant under the delta move. Again, this is a goodness test for not invariants. So there is an unpleasant move, which is very similar to the third Reidemeister move. However, it's bad. And actually, if you're not is invariant under this, if your invariant doesn't change under this delta move, then somehow it's not a very good invariant, and our invariant passes this test. So it changes under this move. And actually here you should take care about not only these directions, these chords. So if you have a 7 chord, you should also take care of what intersects this chord from the right to the left and what intersects it from the left to the right. Actually, so we can test this. So there are many tests for not invariant to be good. For example, invertibility and other things. And for example, this delta move, it's not invariant under the delta move. Okay, and starting with winding number, which is just a Z invariant, we can why it is good to get this invariant, because it's cobordism friendly, and the instances of those cobordism friendly appeared maybe 10 or 15 years ago, but they were considered for more abstract objects. Here we deal with more concrete objects. Well, actually, something similar with those secondary indices were constructed by a mathematician from Beijing, Chen Jiyun. And actually, his invariants were invariant under the delta move. And well, of course, I'd say some words about group valued invariants, and we can get group valued invariants, but it's technically more different. And actually, in fact, whenever in topology we have something like Z2 homology or Z homology, we should find indices or secondary indices. I think that it should work for 2 nodes. Actually, if you ask more, I think they should act whenever we have some characteristic surface, maybe codimension 1 surface. You can look at some winding numbers by intersecting with some codimension 1 or evaluating some cohomology class. And all proofs here are easy. So these are proofs like look at 7, 3, and 4, and 7 changes indices with 3 and 4, changes incidences with 3 and 4, and this doesn't change the parity or something like that. And for groups, it's also free. It's also easy. And lots of generalizations, so we can count and count and count again, secondary indices, ternary indices, and so on. And here is an example, which is due to Kim Sarah, that it's not invariant under the delta move. Yeah, just this is a matter of count. And now I want to pass to the last part of my talk, is about sliceness. You see, in low-dimensional topology, sliceness is a very important thing because in dimension 4, smooth structures is not the same as topological structure. And actually, we can see it somehow from the point of view of knot theory, because if we have knots in just a 3, they can be topologically slice. I mean, slice in the locally flat setting, but not smoothly slice. So by Friedman's theory, we see that if a knot has Alexander polynomial equal to 1, then it's topologically sliced. On the other hand, there are nice invariants like Rasmussen invariant coming from Khovanov homology, which gives an obstruction to smooth sliceness. But you see, Friedman's theorem contains a very hard techniques coming from Kesson handles and some very non-smooth topology. And Khovanov homology, well, it's completely combinatorial, but at least it uses some formal complex cell complex techniques, and it's very much non-polynomial. I would say that it uses invariants which are hard to compute, and Rasmussen invariants are not easy to describe to an undergraduate, for instance. Rasmussen invariants use spectral sequences. And the invariant, which are more or less already introduced, I mean, this count of some crocodiles or elephants with indices and maybe with Z2 coefficients. So they are easy to compute. We just look at a chord diagram and we can teach our computer what to do. Just look at chords and count some numbers and count some numbers further, and this will be an invariant. And actually, this gives a sliceness obstruction in the thickened cylinder. So actually, the slogan is find some Z homology and make sliceness problem easy. So by technical reasons, I'm still in the cylinder and I need this homology, but it's easy. I'm pretty sure that in some steps it will be overcome and it will appear for just knots. And actually here I have a knot in the full torus. I just multiply this full torus by an interval. And actually what I want to say is that if our bare count of something is non-trivial, then our knot cannot be sliced. Actually, what about the proof? Well, actually, the proof is more or less follows the standard topology course when we prove that something like linking number or maybe mapping degree is cobordism invariant, or maybe not cobordism invariant, but it's invariant under homology. Okay, so how do we usually prove that? A mapping degree is invariant? So we usually draw something like a cylinder. Okay, so here we have a mapping degree. Here we have a map, and here we have a map, say, from a circle somewhere, and we want to look how many times we intersect how many times we intersect the international date line, for example. We can intersect it positively and we can intersect it negatively. So we can say, okay, let's count some numbers. Let's count some numbers and say that the total number doesn't change. So usually there is such a picture, well, at least as it's taught in Moscow, in the Moscow State University. So we can have, for example, some curve here, and we count some numbers, some intersections with something of codimension 1, and we can have a curve down here, and we count something of codimension 1 here, and we just connect these things from the top to the top, from the top to the bottom, and from the bottom to the bottom, okay? So this, we can have some things like that. And then we follow some orientation and say, okay, if we have plus here, it can be connected to plus here. But if we have plus here, it can be connected to minus here, and so on. Okay, so plus sign either gets to a plus sign on the opposite side, or it gets canceled with a minus sign. So the total Z count is like this. So this is the usual proof. And then we can say, okay, if we have a disk, and this disk spans something, and we have something like winding numbers, then some double lines on the disk will also have winding numbers. And for example, double lines on the disk, if we leave not just in the free ball, but if we leave inside the cylinder, inside the torus, so these double lines may have some label, like label 7. And then we can say, okay, we intersect something of label 7, positively or negatively, but why don't we count the number of times that we intersect something of label 7? So then we can have, okay, here we have secondary indices. And later on, ternary indices and quaternary indices. And more or less this is a picture, and this says that if we have not just here and not downstairs, then we can just isotope our curve inside the second thickened cylinder, and we isotope and isotope, and we can write down this count of secondary and ternary indices, and we just look at the fact that those secondary and ternary indices do not change. For example, if I say that my 734 can switch their adjacencies, so at the level of chord diagrams, this means that we have a 7 chord which gets canceled. Excuse me, a 7 chord which changes its adjacencies with 3 and 4. So this is like that. And if we are on a 2 disk, so this means that we pass through a triple point. So this is a triple point like 7, 4, 3, and at some point we can say, okay, our red line intersect my 7 chord here, or it can intersect my 7 chord here. So more or less here I would say that this 7 does not intersect 3 and does not intersect 4, and this 7 does intersect 3 and does intersect 4, which means that here we take 0 plus 0 is 0 mod 2, and here we take 1 plus 1 is 0 mod 2. So here we not just count 7, but we take 7 with further specialization. So this can be 7 with 3, 4 index 0. So actually, this is the proof of the theorem. So here we take this count, and this count doesn't change when we take the homotopy of our curves. Okay, so now this is more or less the end of the proof. So we have double lines. So this is the proof written accurately, and enhanced winding number, which is something like 7, 1, 6, 2, 5, 3, 3, 4, and so on. And here is the formal formulation of the theorem. So we have a huge collection of things and we count them mod Z2 and we get a cobordism invariant. So of course, we can say that we take a cobordism between something and the empty set, or we can say that we can take a cobordism between two knots. And in one case, this is a sliceness obstruction, and in the other case, this is a cobordism invariant. So we can take this, and the invariant on the top will be equal to the invariant on the bottom. And again, we get a huge amount of sliceness obstructions for knots in the thickened cylinder. Okay, and now some problems for students and maybe some work in progress. Actually, once we have something like Z2 indices, we can unravel it and get lots of Z indices. So if there are students having master project, I can say, okay, if we have just Z2 homology, we can do some Z homology. Well, not exactly Z homology, but some parity, which counts something like, Z groups. Actually, from the point of view of group theory, I would say that if we take some group like Z star Z, Z2 star Z2, excuse me, this group will have a Kelly graph like this, and this Kelly graph from the infinity looks like Gromov's. Looks like the straight line. And on the straight line, we can have Z indices. For example, from here, we can get here, and this is somehow 2 or maybe 1. So the group here is commensurable with the group Z. So this is how to get Z from Z2. And actually, we can get lots of cobordism invariants. So ternary, quaternary, but already this secondary things give lots of obstructions. Also, there is a problem about hidden crossings. Well, in fact, once you have a cylinder, you can draw quite a lot. You see, once I said about the front part and the back part on the cylinder, and if I draw something here on the front part, I can say, okay, on the opposite side, on the antipode of the cylinder, I can have a point, but I don't count this pair of points as a crossing because they are at the distance of angle pi. But we can take not only the angle pi, but something like 2 pi over 3, 2 pi over 5, and so on. So we can get fancy indices mod p or mod any other number. And actually, this again gives rise to many indices, parities, and so on. And this can again be a student project. And actually, more brackets, more parities, and other things. So in knot theory, there are lots of invariants which are calculated as follows. We take a knot invariant. We take a knot and draw lots of diagrams and start evaluating this according to some rules. And if we live on the plane, then this rule lead us to a number or to a polynomial. But if we are not on the plane, already on the cylinder, then we can evaluate pictures just to pictures. And lots of invariants can be got this way. So projects and further dreams. Well, of course, classical links and classical knots are just a problem of technicality. Maybe here I want to say classical links and classical knots in S3, not in the cylinder. But then you can ask, well, where to take this Z homology class? Well, I can say let's go around this knot, and this is a source of Z homology or Z2 homology. But if we go around this knot and the knot is not trivial, maybe there is no nice surface to project onto, because if we are in the complement to the unknot, we can project to the cylinder. Or even we can project to the full torus because S3 is S1, join S1, and this means that the complement to a knot is easy. But we don't have an immediate projection, and this is a technical thing. Actually, now I want to say that lots of things in low-dimensional topology can be calculated via knots. So what do I mean here? Actually, here I mean that there is a Kirby calculus for 3 manifolds, and there is an Agbolut calculus for 4 manifolds. Roughly speaking, we can say, okay, all 3 manifolds are knot diagrams modulo something. I would say that 3 manifold is a knot diagram, well, up to some small lie where I should take into account something like framing. Knot diagram modulo not only Reidemeister moves, but also modulo Kirby moves. Reidemeister moves and Kirby moves. And as for Kirby moves, so there are 2 of them, and the first one is similar to Reidemeister 1. It's easy, and the second Kirby move is something like swallow move. So we have an elephant here, and we have a snake here, and the snake wants to swallow an elephant. So we have this, and we just follow like this. So we go along this thing. And you see, it's easy to construct lots of knot theory invariants. But it's not so easy to make this invariant work under this Kirby move. Why am I saying that? Well, because in knot theory, we can take just Jones polynomial. But it's known that that it's very hard to get a polynomial invariant for 3 manifolds. For example, the well-known Witten-Reshetikhin-Turaev is not an invariant valued in polynomials. This can be done only at some roots of unity. Actually, this Kirby move is a very hard thing. But now I want to tell about some easy plan what to do. If we have a, say, fundamental group, then we can say, okay, the fundamental group of my 3 manifold is an invariant of a 3 manifold. Everyone could say it's easy. We already knew that. We already knew that the fundamental group is an invariant. Well, but why is how to calculate, say, a fundamental group? We can say, okay, we are performing some surgery, which means that we take a cycle inside this manifold, we take yet another cycle, and we cap them, which means that we take a certain nice group, maybe Z star Z, and maybe we cap something but by disk, so we take a quotient group. Okay, but many people can say, okay, we know that a priori this invariant will be something topological and well known. But you see, the invariants I was constructing here are not immediately topological and well known. For example, the invariants I was constructing here are just group valued invariants, but they are not a fundamental group. They are valued in something like Z times Z times Z, or maybe Z2 times Z2 times Z2. So my invariants are valued in 3 groups. And if I want my snake to swallow my elephant, I can say, okay, so here we have a group element, and here I have a group element. And for example, this is A, and this is B. And I can take a free group here and take the quotient by A and B. And more or less, the Kirby move invariance looks like that. We take a free group like this, and we take its quotient over A and B. If I just want to swallow my elephant, this means that instead of taking the quotients of A and B, I take the quotient over A, B, and B. So this is something like we see in Morse theoretic argument when we slide a handle, or in some Alexander polynomial invariants when we take some elementary row operations, when we take a sum of one row with another row. So if we have a complicated knot invariant or a complicated three-manifold invariant and we describe it combinatorially, we often see such a move. But you see, these invariants, which are valued in free groups, they somehow imitate the fundamental group, but they are not a fundamental group of anything. Well, maybe they are some fundamental group of something, some specific characteristic element of some tower of coverings, but this is defined very combinatorially. So that's why we dream and work towards three manifold invariants. And actually, for four manifolds, we have an absolute calculus. And we do know that our invariants are cobordism friendly, so we expect we can have many things in these situations. Of course, once we have a direct product with S1, we have something to project onto, and it's very easy to realize many things. Of course, if we have braids with trivial components, for example, Brownian braids, then it's good. Then we have something to project onto. And also, I want to recall a very famous joke due to Lord Kaufman that categorification originates from cats. So instead of just drawing invariants which are valued in say numbers, we can try to categorify to make these invariants valued in some linear spaces, and for numbers we don't have maps between them, and for linear spaces we do have maps between them. But why just linear spaces? Why not to consider invariants like groups? And you see, for linear spaces we have maps, but for groups we also have maps. And you see, going along a path, we can write down an element living in a free group, and it behaves nicely under cobordisms. So this should give us a categorification. Okay, well, maybe I may skip this a little bit just by saying, instead of getting numbers, we can count everything by cats. And maybe my time is up, and I'd like to thank everyone and stop here.
Thank you very much. Any questions or comments?
Okay, maybe you can unmute your microphones if you have questions.
Yeah, so I don't know if this question makes sense, but I'll ask it anyway, because whilst everyone else is still thinking of this. So, I mean, at the end, you gave this sort of nice philosophical picture about, we shouldn't just stick to linearly algebraic invariants, and why not use things? I mean, it feels like parts of this is sort of like trying to, instead of doing something like a universal coefficient theorem for homology, you're doing some sort of group valued, almost like homotopy theory for.
Yes, and actually, one of my dreams is to construct non-commutative homotopy, in the sense that, well, okay, we have a very complicated moduli space, and we want to construct a knot invariant by, say, counting moduli space of solutions to some PDEs. And okay, we take some 5-dimensional things and some things of codimension 5 and intersect them. And we see that here we have 5 numbers, but maybe we can thread 5 points, excuse me, and maybe we can thread through this point by a circle and say, instead of just 1 plus 1 plus 1 plus 1 plus 1, we can say, okay, A times B times C times A to the minus 1 times B to the minus 1, and make them non-commutative. To create something like a homotopy, so to make intersection forms being valued in non-commutative groups. So philosophically, it's like this. And of course, we start from a very low dimensional topology, I mean knots, And we go further. So these are now ongoing projects. So 3 manifolds, and then maybe other things. Actually, we are working with Lou Kaufman, with Sergei Gukov now.
Yeah. I guess I do have sort of like a naive question in terms of, let's say that at some point, you know, through a lot of hard work, we build up this beautiful machinery and this beautiful categorification. We work out all the structures. I guess one of the strengths of linear algebra or just things which are commutative is that there's the ease of computation and that we can compare things. Are you aware of things like normal representations and things like that in the theory that you're trying to build here?
You see, I'm not working not only with non-commutative groups. I'm working with more or less free groups. So, so my groups are easy to work with, and they're powerful.
I see. Okay. Okay, thanks. And I guess another naive question is, do you think that there's any chance that we can take some of these, like the invariants that we build and the theory that we build, and then to do some sort of reduction or like, you know, get rid of some of the complexity and re-understand some of the topology of the knot itself?
Well, for me, the complexity is something like crossing number. And we can say, okay, here my commutative invariants say that we have, say, 2 positive crossing numbers and 2 negative crossing numbers. They get canceled and we get 0 and we don't know anything. But in the non-commutative setting, we have, say, A, B, A to the -1, B to the -1, and in the free group, it's reduced. So in some sense, these commutative estimates from below, like crossing numbers, they appear like this. And you see, one more slogan is try to find a good substitute for crossing numbers. Because why, for example, it's technically difficult to realize something for, say, complement to the trefoil. Because the complement to the trefoil is not immediately, say, something which has a projection. But possibly we should count not crossings, but some other instances of intersections in some other moduli spaces. And possibly you can say, okay, this is 7, this is 4, this is 3. And they go through each other. So for me, it's now interesting to look at, for example, trisecants or quadrisecants of a knot and how they behave with respect to each other. So what are, for example, 7, 3, and 4?
I see. Okay. Yeah, I think that makes sense. Thanks.
I have a question.
Okay.
Did you compute the not cobordism group and then cobordism invariant and not generators?
So what's the question?
Did you compute your not cobordism group and not cobordism invariant and not generators for the cobordism group?
Oh, well, I'd better say that somehow my invariants are sort of estimate from below. They work nicely when we want to say that the cobordism group is by no means, that we have something like infinitely generated things or some other. But so far, they are not good enough to say that we exactly have this much. As I said in the very beginning, we have something which is non-trivial with probability 1, which more or less says that something is infinitely generated. But to say that our invariant is complete, well, some efforts have to be undertaken, and I'm not going to go into the detail. It's a harder question. So just to prove that these are all generators and there's nothing else, well, this is a sort of question similar to well, are not detectors. So we should somehow be able that if we have something in the free group, then if something has no parity at all, no homology at all levels, then somehow it has to be cancelled. This is more or less morally at this level. So we can create huge number of invariants. Yeah.
Okay. Can you produce characteristic class for nodes using your method?
Well, I hope yes, but every day I have only 24 hours. So now we are working hard with Sandron and Serha. I mentioned some other collaborators, so why not? We can go further.
How to produce 3-manifold and 4-manifold invariants using your knot invariant?
Well, you see, through the Kirby calculus. So we know that 3 manifolds are knots modular Kirby 1 and Kirby 2. And so usually people can write down words corresponding to components. And this is an ongoing project. We can discuss it separately, but what is important here is that we are doing not the fundamental group. We're doing some concrete finite group. So my expectation is that the invariant we're going to construct now will be the quotient group of the fundamental group by, the quotient group of the free group by something corresponding to components. But this something is not of the topological nature. It's of something of the combinatorial nature. And for 4 manifolds, well, 3 manifolds correspond to surgery, Dane surgery, and 4 manifolds correspond to cobordisms. So we paste handles to the 3 sphere and then paste a 4 handle. So look at Agbulut's book.
Is your invariant related to the separate invariant?
Well, I have no confidence about that. And actually, you see, here I don't have any. So in my invariants, I don't use any objects of complicated nature. I mean, I don't use any PDEs. I don't use anything coming from these hard techniques. But if I do have something like intersections between moduli spaces and something else, if I take, say, Chern classes of, so first I have to realize what are Chern classes or what are Stiefel-Whitney classes, and then if I can upgrade them to non-commutative things, then I will be happy. And then I can say, okay, I have this moduli space, and then I evaluate some Chern numbers somehow. But I can say, okay, and what about non-commutative Chern number? I think this is a question which can be of its own importance. And if I have it of its own importance, maybe I will not have a desire to look at Zyberg-Witten invariants. Maybe I will, I don't know.
Thank you. Any more questions? If there is no more question, let's send Professor Vassily Manturov again.
Thank you very much for listening, for coming.
Nice. Well.